Hello. Okay, so this video is all about continuity versus differentiability. Okay, so continuity, we should already have a pretty good idea about. Basically, as long as you are sketching a function, if you never ever have to lift your pencil over some interval, then the function is continuous over that interval. Okay, now differentiability. Well, derivative is slope. Okay, so for the slope to exist, the derivative or the slope has to have one value. Let me write that down. For the derivative to exist, let's say at x equal a, then the slope of f at x equal a must exist and must take only one value. Only one real value. Okay? For the derivative to exist at x equal a, then the slope of f at a must exist and must take only one real value. So let's examine some situations where this happens, and let's look at some situations where this doesn't happen. Okay, so I'm gonna plot some stuff here. Okay. So everywhere here to the left, the derivative exists and is only one real value. So everything's continuous, everything is smooth, and the derivative is only taking one value. Now over here to the right is where stuff's going to start to get a little interesting. First, let's look at this situation. This is called a corner. Okay, this is called a corner. Let's keep that in mind for now. Okay, let's say we have another corner here. And let's say the function goes to positive infinity here. Okay, all right. Let's talk about this for a minute. So, first of all, this entire weird looking curve here, the whole thing from the left to the right. So from here all the way here, this curve is continuous. The curve is continuous. Okay, let's look at the corner. Let's look at the corner. Okay, look here. Here's the corner. Now, the derivative is a limit. The limit has a left-hand limit and a right-hand limit. And the way that we can think about the derivative being a limit and the derivative being slope, the way that we can reconcile both of these things is just by considering the left slope and the right slope. So, in other words, here's the blue point. If I look to the left, The slope here is clearly positive. If I look to the right, the slope here is clearly negative. So what happened at the corner? At the corner, the slope instantly went from positive to negative. It did not smoothly go through 0 first. It just, at one instant, changed from positive to negative. So the point there is that the slope is not continuous. Okay? Because the slope immediately went from positive to negative, that means it had to skip 0, and it had to skip some other numbers too. So the slope is not continuous. Okay? Reason. Left-hand slope. Left slope not the same as the right slope. Okay? If you look, okay, let's compare that to this down here. Here's a minimum. And at the minimum, we can visually see here that the slope at this minimum is 0. Okay? Furthermore, if we move barely to the right, the slope is barely positive, and if we move barely to the left, the slope is barely negative. Okay, so in other words, in this little region here, the slope changes from negative to positive, but it does so in a smooth, continuous manner. Okay, so if you see a smooth curve, its slope is going to have one value all the way through that curve. But if you see a corner, that means that the slope instantly went from positive to negative or negative to positive. Okay? Also, as this function tends toward infinity, it appears that the slope does as well. And I'll be honest with you, here in this particular example, there's not enough information to conclude one way or the other. But okay, here's what we can say for sure. Okay, let's look at this. Let's look at the tangent. Let's look at the tangent. Okay, so if we look at the tangent looks like this, sort of like x cubed, but it's periodic. Here's 2 periods of the tangent. Not the neatest graph in the world, but there's like 3 periods of the tangent. And what we know is that, for example, here at negative pi over 2, and here at pi over 2, the tangent's undefined, right? Because tangent is, after all, sine over cosine. So the tangent is undefined when cosine is 0. Okay, so the cosine, right? Cosine is the x component of the r component. And so, whatever angles have an x component of 0, and that's going to be that one and that one. So that's pi over 2 and negative pi over 2, which is where these asymptotes are. Okay, tangent is undefined at pi over 2 and negative pi over 2, and so is its derivative. Okay, so the slope, here's the point, the slope at x equal pi over 2 and at x equal negative pi over 2 and so on does not exist. Okay, because f is undefined. F is undefined there. Okay, so if there's no function to speak of, then there's no way to calculate the slope. You have to have a function first to calculate the slope. And the function has to be continuous. Okay, so if you're asked to calculate the slope at x equals 3, and the function is not continuous at x equals 3, then there's no way to talk about the slope. Okay, so these are just different conditions where the derivative doesn't exist. One condition, right, is if you have some sort of corner. And then the other condition is if f is undefined or if f is not continuous at that particular value. Okay, let's draw another little example here. So we could have something like this. Okay, so, if this is, well, I don't know, let's say this is x equals 3, for example. So at x equals 3, let's say this is f of x. F is discontinuous. It's a jump discontinuity here. Okay, at x equals 3 we have a jump discontinuity. And so the derivative, which is the slope at x equals 3, does not exist. Okay? 1, we have discontinuity, and 2, the left-hand slope and the right-hand slope are not the same. Okay? So there we go. So this kind of covers the situations where your derivative is not going to exist. Let's see, what about the last situation? Let's talk about this last situation here. Let's say we have this. So we have something like this. So here we have a hole. Sorry. Okay. So here, where the hole is, we have a, just for simplicity, let's say this is x equals 3 again. We have a hole at x equals 3. And so dy dx does not exist at x equals 3. Well, actually, let me get back to you on that one.